Welcome to Spectroscopy video number 4. The focus today will be on NMR, Nuclear Magnetic Resonance Spectroscopy, which is one of my favorite forms of spectroscopy. A little bit of chemical humor. There's some interesting structures here. My favorite is kauninol. A common theme in this unit for accessing prior knowledge is remembering your organic chemistry structures, functional groups, but not just functional groups now, but really the entire structure of an organic compound. Same big ideas. This is video 4 of the series related to spectroscopy. Same big ideas. Here the focus is on NMR. There is one NMR bullet point that we will save until the next video, but we are focusing on what is called proton NMR. But first, the real key to proton NMR is understanding the chemical environments for the hydrogen. And I've drawn a molecule here. I'm not even sure I want to name it. I've drawn a molecule here to show you different chemical environments for hydrogens. So if I start with these 3 hydrogens, they're all connected to the same carbon, therefore they are all the same chemical environment. So this hydrogen is connected to a carbon, which is connected to an oxygen carbon, and this carbon is also connected to 2 hydrogens. Now, if I look at that same sorry, I was trying to erase some of my writing. I guess I can't. If I look at this hydrogen, it's connected to a carbon, which is connected to an oxygen carbon, which is also connected to 2 hydrogens. So notice that when I described this hydrogen here, I had the same pattern as when I described this hydrogen. And it will be the same pattern for this hydrogen. So these 3 hydrogens all have the same chemical environment. But this hydrogen is connected to an oxygen, which is connected to a carbonyl. It's the only hydrogen in that environment. This hydrogen is connected to a carbon, which is double bonded to another carbon and bonded to a carbonyl. But this hydrogen is bonded to a carbon connected to a double bond, but connected to another carbon that has 2 carbons and an oxygen. So these 2 hydrogens are actually different. However, these 3 hydrogens and these 3 hydrogens are all the same, because these bonds can rotate. And so that means if I describe this hydrogen is connected to a carbon that's connected to 2 hydrogens, which is connected to a carbon with a carbon, and oxygen. Well, this hydrogen is connected to a carbon connected to 2 hydrogens, and that carbon is also connected to a carbon with a carbon, and an oxygen. Same. So these 2 CH3 groups connected to the same carbon are the same chemical environment. So that means there are 6 hydrogens here that have that chemical environment. There are 3 hydrogens here. There's 1 hydrogen there, 1 hydrogen there, and 1 hydrogen there. So 1, 2, 3, 4, 5 different chemical environments for the hydrogens in this molecule. Now, just a very brief look at the workings of NMR, very brief, and IB doesn't even say you need to know much about this, but it does use radio waves, and I think that's maybe something to remember. It does use magnets. A large, strong magnetic field causes the hydrogens to align, essentially, because of the spin of the electrons, and a radio frequency is sent over the sample, and how the hydrogens align themselves affects that radio frequency, and the output can detect different chemical environments for the hydrogens. And that's all you really need to know. You don't need to know anything more. If you want to know more, there are resources that we can share, but that's the key. So, in order to have a standard, there needs to be a standard molecule that has the same chemical environment for every single hydrogen. So, tetramethylsilane, TMS, CH3, 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 all of these hydrogens have the same chemical environment around this silicon. And so that is the standard. And it's analogous to the standard hydrogen electrode, which we will learn about in topic 9 and 19. It is a standard, and it's the chosen standard. Are there other molecules that could have been the standard? Sure. This was chosen because of where it ends up being on the spectrum, as we'll see. And all other molecules are compared to it. Your data booklet actually gives you NMR data, and we will look at the types of protons or types of hydrogens here in the left column, and then the chemical shift on the right. And this chemical shift will make sense when we start looking at spectra. This is all relative to TMS having a value of 0. R represents an alkyl group, and HAL represents a halogen of some sort. These values may vary in different solvents and conditions. So these are guidelines. They are not exact. And we will see spectra that do not follow these guidelines exactly. So let's look at some spectra. Draw ethanal. What is ethanal going to look like? And then consider the number of chemical environments for the hydrogens that you would observe for ethanal. Okay, ethanal looks like this. There's your molecule. Eth means 2 carbons. Anal is an aldehyde. Ethanal aldehyde. It has a hydrogen on the end with a carbonyl carbon. So what we have here is an NMR spectrum. Chemical shift has a scale on the bottom that starts with 0 on the right and moves up from there. And there typically is a small peak at 0, and that is your reference peak. That is your TMS. We have a peak here and a peak here, and these have what is called an integration trace or integrated trace, and that gives the relative number of protons or relative number of hydrogens. Approximately, it's the area under the curve. So this peak is worth 1 hydrogen, and this peak is worth 3 hydrogens. And the integration trace, we will either be told the number of hydrogens for each peak, or we will be given a trace, and we compare the relative heights. This height is 3 times as big as this height, so it's 1 to 3. And 1 to 3 makes sense for ethanal, because this hydrogen is a single hydrogen in its own chemical environment, and these hydrogens are in their own chemical environment as well. Each of these 3 hydrogens is the same chemical environment. So there should be 1 peak that's worth 3 hydrogens, and there should be 1 peak that is worth 1 hydrogen. And if I look at our data booklet, CH3 tends to be about 0.9 to 1. Well, this one's above 2, but it's the only peak that could be for this trace that could be the CH3. And so right away we see that these are just guidelines. This peak represents the hydrogen of the aldehyde, typically between 9.4 and 10, and here it is just about 10. So we have 2 peaks on the NMR spectrum representing the 2 different types of chemical environments for the hydrogens. So let's start looking at some unknowns and see if we can start making some analyses. Compound with a molecular formula, C3H8O. So you might consider figuring out the index of hydrogen deficiency and then draw the isomers of C3H8O. That will help as a comparison. And we're given the integration. 2 hydrogens, 1 hydrogen, 2 hydrogens, 3 hydrogens. So 2 plus 1 plus 2 plus 3 equals 8. So these are the actual number of hydrogens. We sometimes will see that these numbers, because they're a ratio, they might match the empirical formula but not the molecular formula. That's just something to be aware of. So draw the isomers. What do you come up with? 3 carbons, 8 hydrogens. That's the maximum number of hydrogens. So they're all single bonds. So these are some choices for you. You can draw propane 1-ol, where we have the alcohol hydroxyl functional group on the first carbon. We can draw propane 2-ol, where the hydroxyl functional group is on the second carbon. And we can draw methoxyethane, which is an ether. Notice that the hydrogens here have been color-coded, so 3, 2, 2, 1. 3, 3, 1, 1. And in this molecule, when I said 3, 3, these two groups of 3 are actually the same. So it really is 6 to 1 to 1. Because this carbon is connected to a carbon which has a hydrogen and an OH. This carbon is connected to a carbon which has a hydrogen and an OH, and they're both CH3s. So that means when I said 3 and 3, it was really 6, because these 3 and these 3 are the same. And that's something to keep in mind every time we think about NMR. Methoxyethane, 3, 2, 3. So if we look at our spectrum, 2, 1, 2, 3. Which structure is the best fit and really is the only possible fit? And it happens to be propane 1-ol. So peak number 1 is 3 hydrogens. Excuse me, it's right here, 3 hydrogens. It is about 1, and that is a CH3. Now, I have 2 peaks here. I have 2 hydrogens here and 2 hydrogens here. That is this peak and this peak. Those are both what's called CH2R, about 1.3 to 1.4, and that's about where this one is. This one's a little bit higher. And then I have a single hydrogen peak, which is this hydrogen on the OH. And OH alcohol hydrogens tend to be between 1 and 6, quite a range. But it is the only peak that can be 1 hydrogen. Checkpoint question. Let's have you try one. Here's the question for you. See what you can do. Pause the video and see what you can work out. Alright, you ready? The answer is C. The peak area corresponds, so that peak area is the integration curve, how many hydrogens there are, 3, 3, and 2. Peak area corresponds to the relative number of hydrogen atoms in that particular environment. So let's look at the molecules here. This is propane. This would be, these 3 would actually be 6 and 2, so that would be 6 to 2. So it can't be A. B would be 3 to 2 to 1. Can't be B. C, these three are the same as those 3, these 2 are the same as those 2, and then those 2 are the same. So I would have 6 to 4 to 2, which is the same as 3 to 2 to 1. So it can't be D. So it kind of has to be C, but let's make it work. 3 to 2 to 3. 3 to 2 to 3. So option C really is the only peak that would work. We have the chemical shift, 1, that's a CH3, probably that CH3. We have another peak of worth 3 hydrogens at 2, probably that CH3, and then we have a peak worth 2 hydrogens, which would be that CH2. And there you have it. In terms of a summary, NMR spectroscopy allows for detailed structural analysis, and that really is the key here. We finally can do really detailed structural analysis, especially when it's coupled with other forms. I did the same typo, I apologize. It's because I copy and paste the same summary starting statement, but this is a different statement. Especially when coupled with other forms of spectroscopy. NMR spectra give information about the chemical environment of the hydrogens in an organic molecule, and that is where that detailed structural analysis comes from. Thank you for listening. Much appreciated. There is a checkpoint question, so I'm hoping that you'll take some time to put your checkpoint question answer into the Google form. Let's raise the percentage of participation. This is Spectroscopy Video 4. You also can ask questions and you can provide feedback. Thank you. Have a great day. See you in class.